Hello everyone and welcome to this lecture. In this lecture, we are going to cover gradient boosting algorithms in great details, and we're going to cover XGBoost as well, which stands for extreme gradient boosting. Okay, so let's get started. So here are the steps for XGBoost. So XGBoost repeatedly builds new models and combine them into an ensemble model. And what XGBoost does, and it's kind of the same idea as well for just the basic gradient boosting algorithms, is that they initially build the first model initially, and then you calculate the error or the residuals for each of the observation. So initially you just come up with certain predictions, and then you subtract the predictions minus the ground truth or minus the actual labels in the training data. And once you have that, once you have these errors or residuals, you build a new model to predict those residuals. I know it sounds a little bit weird at first. It sounded as well a little bit strange to me at first. And I'm going to show you guys example in great details coming up. But that's the idea, is that you try to build based on the mistakes or based on the errors that have been done in the past or in the previous stage. And what you do is that you add prediction from this model to the ensemble of models. And you keep doing that, and over again, you do kind of think of it as kind of very small steps toward the ultimate truth. And that's what you're trying to do. So XGBoost is actually superior compared to gradient boosting algorithm, since it offers a good balance between bias and variance. So actually gradient boosting only optimized for the variance, so they tend generally to overfit the training data, while XGBoost, they offer regularization term that can improve model generalization. So let's take a look at the actual kind of process or steps from a very high level. So first, you start with initial model. Think of it as kind of a starting point first. And what you do afterwards is that you calculate the errors based on the previous model residuals. So what you do is that you go ahead and you subtract what the model is predicting initially minus the labels or the ground truth. So now you have a list of residuals or errors. And what you do afterwards is that you build the model to predict those residuals from the previous stage. And once you have that, then you add the last model to the ensemble, and then you repeat again. Make new predictions, calculate residuals, and develop a model to predict those residuals. And then you keep repeating again. You add that to the ensemble, and you keep going, moving on and on and on, until the actual model becomes way extremely powerful. And think of it as kind of combining all the intelligence from all these weak models to come up with a lot more superior model at the end. So let's take a look at it graphically. So that's what happened. First, you start with an initial guess. Think of it as kind of the average, let's say, of all predictions initially. And what you do is that you build a tree, okay, and you scale that tree as well. So we scale it with what we call it a learning rate. And that learning rate will adjust or will ensure that our network is not overfitting the training data. And what you do afterwards is that you take the errors based on the predictions coming out from here, and you build another tree. So here I have another tree, and you scale it as well with a learning rate. And then you create another tree based on the errors from the previous one or the predictions coming from the previous stage. And you scale it up with a learning rate, and you keep doing that over and over again. And you are basically, think of it as kind of combining or making like a massive model that is learning based on the previous and mistakes from the other previous models as well. I know that that's, again, sounds a little bit strange. So let's take a look at a deep dive example that will show you guys how gradient boosting algorithms works in great detail. So let's get started. So this example has been adopted from the awesome StatQuest by Josh Starmer. It's actually an amazing channel. I highly recommend that you guys check it out. And I found a great example there, and I'm including it here. So let's walk you through it. So gradient boost works by building a tree based on the errors or residuals from the previous tree. Okay? And gradient boost scaled the tree, as I mentioned here, we scale it up with the learning rate, and then adds the predictions from the new tree to the predictions from the previous tree. So let's take a look at an example. Let's assume that here I have height, I have my color, I have my gender, And these are the independent variables. These are the input features. And what I'm trying to do is that I'm trying to predict the weight. That's what I'm trying to predict, okay? So basically, this is a prime example of a regression-based problem in which I'm trying to predict a continuous numeric output, as you guys see here. So what XGBoost do, or gradient boosting algorithms will do, it will just gonna build a tree first. So let's see how I'm gonna actually make the predictions step by step. So let's take a look at it. So let's assume that we wanna make just initial predictions in the beginning. So what I'm going to do, I'm gonna go back here. I'm gonna say, okay, let's go ahead, take a look at all these predictions, 88, 76, 56, and so on. And let's go ahead and average them. Just, like, again, I don't know any better. I don't have any historical data. I don't have anybody to learn from. I just want to create a very basic model. So the model will say, you know what, I'm just going to average all these values. And that will give me here 71.2. And that will be my initial starting point, okay? So this is the first step. The second step, as I mentioned, is we are going to go ahead and actually calculate the error from this prediction. So what I'm going to do here is, again, I have my input features. Here I have my weight, which is my ground truth. That's what I'm trying to predict. And here, these are my predictions for all the points, right? That's what I'm trying to do here. So what I'm going to do is I'm going to say, okay, these are the model predictions. This is the ground truth. Let's go ahead and calculate the error, which is a difference between the true minus predicted. So I'm going to say, okay, take my true value, which is 88, minus the initial predictions first, which is 71.2. That will give me 16.8. And then you subtract 76 minus 71.2. That will give me 4.8. And so on. And you will come up with a list of errors or residuals. So again, here we haven't built any trees yet. All what we're doing is just a very basic predictions based on the average. And when there, we calculated the residuals for my initial guess or my initial predictions. Pretty simple. And what we're going to do here, and this is the tricky part, we wanted to build a tree, okay? And that tree will be based on these residuals. The tree is trying to predict those residuals. So let's take a look at it. So here is my tree. So it's the tree first. And please note that here we are just limiting the tree to only having 4 leaves at the end. And let's take a look at it first. I'm going to say, okay, here I'm going to see if my gender here is male or female. So I'm going to say if is female. So female here, female, and here we have female as well. So I'm going to say, okay, is female, yes or no? So if it's yes, then I'm going to have another check. Is my height less than 1.6 or not? So I'm going to go here. I'm going to say, okay, is this female? All right, that's yes. So we're talking about this row and this row, and I have this row as well. And I can check, is my height less than 1.6? So you will go ahead here. You will say, well, this one is less than 1.6. So here I have the residual is minus 15.2. So I'm just going to go here and add minus 15.2. And similarly, I have, again, female, and my height is 1.4, which is less than 1.6. Then I will add it here. So now I have minus 14.2 as well in this leaf. And I will actually do the same as well for all the trees. So I'm going to come here and say, okay, is the height less than 1.6? I'm going to say no. Again, within the female here. And that will generate the 4.8 value that I have in here. I will do the same as well, but for the color now. I'm going to check on the color. So I'm going to say, okay, is female? Will tell me no. So now I'm talking about this male value, this male value, and this male value. I'm going to say, okay, is my color not blue? So any other color? So I'm going to tell me yes. So now I'm talking about the green color. So I'm talking about this one and the red and green. So I'm talking about these two, this row and this row, which indicates 1.8, which is what I have here, and 5.8, which is what I have here as well. Well, if my color is blue, yes. So I'm going to go here and that will give me 16.8, which is what I have here. So now I have male and blue color, and that's what I have here. Okay. So this is simply a very simple basic tree, and that's simply how we actually build our tree based on the residuals, and that's very important. So if you guys notice here at the end, I didn't include the predictions, I actually included the residuals, okay, and that's the very important point. So if you take a look at it here, you will say that first, we limited the number of leaves, or restricted to be 4, just for the sake of simplicity. And what I'm going to do here is that I'm going to replace the values with the average. So as you guys see, because here we have only 4 leaves, you will end up with these values in here, right? So I need to average these values. So I'm going to go ahead and average minus 15.2 minus 14.2 divided by 2. That will give me minus 14.7. And I'm going to, again, I'll obtain the other average for these two values. 1.8 plus 5.8 divided by 2 will give me 3.8. And now I have this tree right now, okay? All right. So what I'm going to do right now, and that's very important, and that's how gradient boosting algorithms work in general. I take the initial guess that I had before, and I'm going to add to it the predictions coming out from my tree. Think of it as now for each of the data points, I can go ahead and go down the tree and see what are the values that I'm trying to predict. That's all what it is. So if you guys take a look at it, you will say, okay, let's take a look at the first point. So I'm going to say here, I have 71.2. I'm going to say plus, and I'm going to go here and see, okay, which one does it belong to? So basically, is female? Well, that's no, because I'm talking about the first row, it's male. And then is not blue? I'm going to go ahead here and say, well, no, because it is blue. So I'm talking about the color blue. So that will give me here 16.8. So I'm going to go ahead and create new predictions. So I'm going to say, okay, it's 71.2, which is what I had before, plus 16.8, which is the value that I have here. And that will give me 88, which is exactly the same as the weights, which is as the actual ground truth. So some people might say, you know what, that's amazing. Now you have been able to just go ahead and just achieve what you're looking for, is to get the exact same predictions initially. The problem with this strategy is that if you actually do this without doing any scaling in here, that will make the network try to overfit the training data. So now my data, basically now I have a model that learns exactly the training data and it just fails to generalize. And that's the beauty of the gradient boosting algorithms and XGBoost, is what we do is that we try to actually go ahead and scale it somehow. So we're going to go ahead and add some scaling factor in here to scale the predictions. And instead of just going and shooting like crazy and reaching our target in the first run, we're just going to take like small steps, just baby steps. Think of this way. So here the model predictions matches the true weight. And this indicates that the model is overfitting the training data. So instead, what I'm going to do is I'm going to take, again, my initial or my average weight, and then I'm going to add a learning rate. We'll call it 0.1, for example, and then multiply that by the predictions going down the tree that I got for every data point. So when I actually do this, I can go ahead here and can say, okay, now my new predictions are 71.2, which is what I had before, plus the learning rate now, which is 0.1, times 16.8, which is simply, if I go down the tree in this fashion, I will come up with 16.8, and that will give me 72.9, which is perfect. So what we have done here is that we added a learning rate, which is a number that range between 0 and 1, to overcome this issue. And this parameter is used primarily for scaling purposes, by trying to adjust the newly added information from the new tree. And adding this tree and scaling it with the learning rate helps us get closer to the true values. Think of it as kind of taking smaller steps or baby steps, and that will help us avoid overfitting the training data. Okay? All right, let's take a look and actually do that for all the points. So if you go ahead here, you will notice that we have came up with the new residual. So now I have new predictions, again, that which is what we obtained, 71.2 plus learning rate times 16.8. That will give me 72.9, which is what I have here. And what I'm going to do is now I have new predictions, right? I can go ahead and calculate new residuals. Okay, so now I have the initial residuals. These are the initial values from the average. If you guys remember, these are what we got here before. These are the initial residuals. These are the values here. We had initially based on the fixed prediction values of 71.2. So we call these kind of initial residuals here. So that's what I have here. These are the initial residuals. And now I'm actually calculating new residuals. That's what I have here. And you guys will notice that the actual new residuals are actually less than the initial residuals. And that's a great accomplishment. Now we have been able to actually get a little bit closer to the ground truth. So now 16.8 becomes 15.1, and 4.8 becomes 4.3, minus 15.2 becomes minus 13.7, and so on, which is amazing. That basically means that we're getting closer to our true predictions. And that's it. You keep repeating and repeating and repeating, and that's what happened here. As you guys see here, we actually take the average weight, we build the tree, we scale it, we make predictions, we calculate new residuals, and we build another tree. We scale it, and then we make predictions, and we build another tree. We scale it, and we keep going and on and on and on. And that's how you actually combine all the intelligence from all these models to come up with an extremely powerful model at the end. So now we can make new predictions by combining all the scaled predictions from all the trees. And that's simply how gradient boost algorithms work in a nutshell. Again, it's very, very intuitive and actually very simple. And that's all what I have for this lecture. I hope you guys enjoyed it. In the next lecture, I'm going to dig into the paper for XGBoost, just give you an overview of, okay, so now we cover the gradient boosting. What about extreme gradient boosting? What about XGBoost? That's a different story. We're going to cover it in the next lecture. In this lecture, we are going to cover from a very high level the XGBoost algorithm. And if you guys remember from the previous couple of lectures that we have covered the idea of gradient boosting, okay? So we actually didn't cover the extreme gradient boosting algorithm. So we have learned that we could actually build kind of a series of trees. As you guys remember here, we actually have our initial guess, we can build a tree, and then we can scale that tree with a learning rate, make predictions, calculate residuals or errors, and then build another tree to predict those residuals. And you keep going on and on and on, and that will generate a massive, a lot more powerful, basically, algorithm compared to only relying on a single tree on its own. And okay, so now we covered gradient boosting algorithms. What about extreme gradient boosting algorithms? So here is a paper that basically summarizes extreme gradient boosting algorithm. And the algorithm has been proposed by Tianqi Shen from University of Washington. And I highly recommend that you guys as well go through the paper. But please know that this paper is not simple. There's actually a lot of math included in it. And I just want you guys to take a look here at kind of the abstract, just from a very high level, what is it or what they are proposing here. So tree boosting is a highly effective and widely used machine learning method. And in this paper, we describe a scalable end-to-end tree boosting system called XGBoost, which is used widely by data scientists to achieve state-of-the-art results on many machine learning challenges. This is actually an important point, that XGBoost has actually been applicable to and won several Kaggle competitions, and they actually try to highlight that here as well. So out of 29 challenges, there were 17 solutions that used XGBoosts of some sort, which is again pretty amazing. And you will find that XGBoost actually either comparable or even better compared to deep neural networks, which is again extremely powerful deep learning algorithms, and we're going to cover that again in the next couple of case studies. So here we propose a novel sparsity aware algorithm for sparse data and weighted quantile sketch for approximate tree learning. So basically what the paper is introducing is that they are introducing gradient boosting trees, but they are also adding a lot of optimization, they are adding a lot of algorithms in there. So it's actually XGBoost, and that's why they call it extreme gradient boosting. It's a collection of algorithms that tend to apply the gradient boosting, yes, but in addition to that, it helps you do that with a much fewer resources, and you can actually do like billions of examples, and that will help you achieve results in a much faster period of time. Again, I highly recommend that you guys go through the paper, but that's again from a very high level. And what I try to do here, I try to kind of outline a couple of key paper highlights. So the most important factor behind the success of XGBoost is its scalability in all scenarios. So they try to build the algorithm by applying gradient boosting while at the same time performing 10 times faster than the existing popular solutions. And the XGBoost could actually scale to billions of examples in distributed or memory limited settings as well. And what they mention as well in the paper is that the XGBoost algorithm actually provide a lot of algorithmic optimizations. So again, there's tons of techniques that has been applied in there. I'm not going to be covering all of these techniques in details. Again, there's a lot of math behind it, but from a very high level, there is a novel tree learning algorithm. There is that could handle sparse data. There is the weighted quantile sketch procedure that enable handling instance weights in approximate tree learning. There is parallel and distributed computing, makes learning faster, and that enables quicker model exploration. Also, which is as well important, is that XGBoost exploits out-of-core computation and enables data scientists to process hundreds, millions of examples using just a basic desktop. And finally, as well, they try to combine all of these techniques along with the gradient boost that we covered before to come up with an end-to-end solution to solve pretty much any machine learning problem, whether it's a classification problem or regression-based problem as well. All right, okay, so that's kind of from a very high level how XGBoost actually works. In the next lecture, I'm going to walk you through AWS SageMaker XGBoost and what instances do we need, what are the input-output data that we need, and now we're going to be pretty much ready to go ahead and actually apply XGBoost using SageMaker. So that's all what I have. Please enjoy AWS SageMaker practical course, and I will see you guys in the next lecture.